We've spoken about how the success of Moore's Law, the successive scaling, the incredible scalability of lithography has allowed us to make these smaller and smaller transistors, these more and more complex integrated circuits. But that's taking us over the precipice well into the nano world, where we've also said the rules are changing. And so in this lecture, I'd like to speak about what happens, how the rules of the nano world become manifest, and both how we can manage them. It's kind of one approach, how we can try to continue to scale, and there's lots of success in continuing to scale, by managing these effects at the nanoscale. And then the other approach, which we can pursue in parallel, and which does get pursued in parallel by researchers around the world, is to try to see what exciting new phenomena are available to us. What's new in our toolkit? What kinds of new classes of electronic devices can we make once we gain dexterity on the scale of a nanometer? So let me start with this first topic of, why is it a challenge? How does the world change when we get down to the nanoscale, specifically in electronics? And to do that, I need to take just a bit of time to describe in a little more detail how one of these semiconductor transistors works. This picture is showing a transistor in a cross-section. And laterally disposed are two electrodes through which current can flow. This is called the channel, and it's exactly as it sounds, just like water would flow through a channel. Here are electrons. Current is flowing through a channel. Now, on top is the control. It's referred to as the gate, and this gate is used to open and close the channel. But the specific mechanism by which it opens and closes the channel is as follows. Through the application of a voltage on the gate, we either attract a sea of electrons into the channel, enabling flow. We fill it up with water, our channel. Or, if we put on a bias, an electrical potential of the opposite polarity, we repel electrons away. Our channel becomes depleted. Current flow is no longer possible. Now you'll see in this image that the gate electrode is separated from the channel. It's distinct. This is referred to as the gate oxide. And this is one of the things that we love about silicon, is one of the things we love about transistors. This oxide is an excellent insulator. It prevents current from flowing from the gate into the channel. That's a good thing. Our control now requires us to expend very, very little current. Essentially, no current flows from the gate into that channel. But through the application of this potential, we modulate the flow. We fill or empty our channel, but it doesn't cost us any electrons. It just costs us the application of quite a small voltage. Now, the other thing that just makes us love silicon so much is that this oxide is, in the case of silicon electronics, it's the native oxide, silicon dioxide. That's great for a couple of reasons. It means that the process by which we grow it is a very natural one. We simply introduce our silicon wafer into a furnace. We introduce the right temperature, the right ingredients in terms of water and oxygen, and we can grow an oxide, and we can grow it on the nanoscale. We can grow it to be a couple of nanometers thick. The other thing we love about it is that that oxide is just inherently disposed to passivate or terminate the states of the silicon that is sticking out of the substrate, sticking out of the wafer. And so we have a natural strategy using silicon's own native oxide for passivation, for termination of these sites chemically, and for the formation of an oxide of essentially whatever thickness we want to grow it to. We just take a bit longer, we just increase the temperature a bit in order to grow a more complete oxide. Now, here's where things start to get challenging. We spoke about scalability, and a component of our scalability was our ability to make many, many transistors on one integrated circuit. But in the course of scaling, we've also shrunken. We've shrunken the lateral dimensions of our transistors to fit more into the same region of an integrated circuit. In so doing, we're forced to scale vertically as well. We are required to make this gate oxide thinner and thinner. Why? This gate has to induce this channel. It can't be too far away from where the channel is located. It has to have that influence for a modest amount of voltage. To induce this very conductive channel, we need to be very close to the channel, and we have to get closer and closer as our transistors get smaller and smaller. So this is a scaling challenge now that we have. Well, what happens when we make this gate oxide a couple of nanometers thin? Well, now we have to think about electrons as waves. Now we have to think quantum mechanically. And if the electron is a wave, as is depicted in this image, then through a very, very thin oxide, thin on the scale of the electron's own wavelength, that wave can be both on the left and the right side of this barrier. It is simultaneously, through the probabilities of quantum mechanics, it can be on the gate electrode where we want it, or this electron has some probability of ending up in the channel. Now, the thing that we loved so much about this transistor model, in which essentially no current flowed into our channel, we got a huge leverage in our switching. It cost us almost no current to switch a very large current. Now that advantage is compromised through tunneling. So this is an example of where quantum mechanics, if we don't change our paradigm, if we don't change our approach, starts to imperil the advantages of silicon electronics. Now, material science and nanotechnology to the rescue here. They have been able to come to the rescue on this particularly important issue. On the left is a transmission electron micrograph of a standard silicon gate. The SiO2, that's the glass. That's the native oxide that's been grown. These TEMs, by the way, are pretty incredible. The structure that you're seeing in these images, these are individual atoms. So with our transmission electron microscope, we're able to image individual atoms. In fact, this is another illustration of our concept from earlier lectures on how small you can confine waves. We're able, using electrons, to see things as small as electrons, to see things on the scale of about a nanometer. There's no way you could take pictures of like this using visible wavelength photons, which are so much larger. Now, so this is showing a gate oxide that's a couple of nanometers thick. And it needs to get so thin again so that we can control, through the gate, we can control the formation of the channel beneath. We can't have our gate electrode be too remote from our channel in order to effectively control it. Now, on the right, you'll see what's called a high K solution. And the high K is referring to putting down a different material with different properties. Folks have discovered how to put down an insulator that resides between the gate and the silicon that can be thicker. You can get away with making it thicker, but it can still induce just as effectively this channel, this inversion region, inside the transistor. And so it's able more effectively to transfer the impetus of the gate. It's able to modulate the current flowing, even though it's thicker. And as a result of being thicker, we've postponed the onset of our tunneling problem. We are able to make this gate oxide thicker and still have the same strength of modulation, but we do so without the cost of having this large current. So these high K dielectrics, these new materials, are very exciting and are very attractive. Now, you recognize, though, what we've done is we've given up one of the things we absolutely loved about working with the native oxide, silicon dioxide. We loved the fact that we could simply grow it and that it could passivate everywhere across our silicon. We could grow it in such a way that it formed itself everywhere across the entire wafer at the same time. As long as there wasn't any dust or anything, there were no pinholes. A pinhole would be an opportunity for current to start tunneling through, so it would be very bad. Now, on the right-hand side of this image, somehow we've discovered how to put a new material onto silicon that's not the native oxide of silicon, and that has to have all of those good properties. Well, this is where there's been some very exciting advances recently in how to put very, very thin, nanometer thin films of different materials other than silicon on top of silicon. And the technique is called atomic layer deposition, and it's incredibly clever. So the materials that constitute these new dielectrics, an example of it is hafnium oxide. And so it's a two-component material. Hafnium is one of the elements in it, and oxide is the other. And folks have figured out through this atomic layer deposition process how to put down exactly one first layer of the hafnium, which then is very prone to react with oxygen, and then to waft over it a little bit of water or another oxygen precursor and react that first half layer to form a full layer of hafnium oxide, and then to start again. And so we are truly building up, layer by layer, at the atomic scale, these perfect materials. And in so doing, we're also able to interface them perfectly with the silicon beneath. And so when we bring in our hafnium, it sees this structure, it sees this texture of the silicon surface, and the hafnium atoms go where they go in response to this landscape of silicon atoms that are exposed. So this kind of control is what becomes necessary in order to manage these interfaces, because a silicon atom with its unpassivated, its unsatisfied electron sitting up is very unhappy. And we have to passivate each one of these atoms individually and extremely well. So this is a great example of where by scaling down, by getting to smaller and smaller length scales, we confronted straight on the rules of quantum mechanics, the fact that the ground is shifting beneath us, the fact that our foundations, our physical foundations, are starting to change, and where Moore's law cannot simply be extrapolated based on the existing material set. But through innovation, through the development of new tools, like the atomic layer deposition technique, we're able to give more runway. You can see that as we go to further and further generations, we're going to start running into more and more problems. But this is a great example of where, a while ago, people called for the end of Moore's law. People said that inevitably it will have to run out. The question is when. But there were people predicting 20 years ago that it would run out within 10 years. And yet these extrapolations have been able to continue till now. They've managed to surprise people. The longevity of the continued, straightforward, direct, challenging but direct extrapolation of Moore's law has surprised a great number of people. In fact, it's interesting to note that when Gordon Moore made his observation in 1965, that from 1958 until 1965 there had been this doubling every year, he did make a bit of a prediction. And his prediction was that Moore's law could be sustained potentially for another decade, until 1975. Well, he's viewed as a very brilliant man for a number of reasons, but the fact that it was sustained for so much longer, and that the challenges that folks had to overcome now at the atomic, at the nanometer length scale, are remarkable, and many, many people have been surprised by this longevity of Moore's law. There's another challenge that starts to exist in these transistors when we make them smaller and smaller and smaller. And this comes from the fact that current can now leak in what we call the off state. And so when we try to turn the channel off, as we make this transistor smaller and smaller and smaller, we can still get, in what's nominally the off state, we can get some flow of current through this very, very short channel. And one of the solutions has been to try to no longer really think of this as just a planar device. It's not just flat anymore. But instead, to start to think about how we can wrap a gate electrode around the sides, around the edges of one of these devices. Now here, ALD, atomic layer deposition, is very much our friend, because we're going to try to wrap things. We can't just have a process of depositing an oxide that's directional, that will only grow vertically. We need a wrapper. We need a nanoscale wrapper. And atomic layer deposition provides a technique where, because we're working with the chemical reactivity of surfaces, because the hafnium atoms will stick to the sides as well as the top, we have a technique that's very prone to creating a nice, compact, continuous, consistent wrapper all the way around the edges of one of these transistors. Now, there is another challenge that comes here, which is we thought we were doing planar lithography, right? We thought that we were just building kind of a two-dimensional circuit. We were kind of working in a flat landscape, and then we were just putting materials here and there and there. But to wrap a gate around the channel involves etching into the silicon. It involves digging down into a little trench. And when we do that, there's the possibility of making damage. We're no longer dealing with something that's just a sort of a straightforward flat structure. We're starting to build in 3 dimensions. We're starting to build almost skyscrapers. We're starting to build silicon structures that have aspect ratios that are tall. I mean, they're very, very small, but from an aspect ratio, from a kind of architectural standpoint, they're starting to get tall on us. And so this advent of 3-dimensional devices, there's also 3-dimensional circuits coming, but this advent of 3-dimensional devices is something that people have been waiting for because they knew that it had to happen, but has been viewed as very challenging. And now this is starting to show its value. It's starting to show that it can be done, and it's starting to show that we are able to continue to extend Moore's law by using these techniques, these new materials strategies, new materials deposition strategies, especially at the few nanometer length scale. But I'd like to go on, and I'd like to talk about how we can do more than just try to sort of extend the paradigm using essentially the same architectures of circuits, and that new nanomaterials can be our friends in trying to extend the run of Moore's law. And here, not extend it by a generation or two, but maybe extend it by many generations into the future. And let me talk about 2 very beautiful and fascinating materials that are seeing great progress and that are showing real promise for extending the run of Moore's law. So the first one of these is called the carbon nanotube. And you can see a picture of here. It's actually a rolled up piece of graphene. In fact, this was the basis for a Nobel Prize in the early 90s for the discovery that it was possible to make these long tubes of a single atomic layer of carbon, forming this hexagonal lattice, and that these could be synthesized, so we could build them, and then they could also be purified. And their purification turns out to be incredibly important. And let me explain why. You can imagine a sheet of paper. Well, let's take an 8.5 by 11. You could roll up from the tall side. You could roll this way. Of course, you could roll along the height of the piece of paper, or you could go to any arbitrary angle and you could roll up in many directions. Well, now let's lay out a sheet of graphene with its hexagonal, its honeycomb structure. I could roll it anyway, but in fact, there's a few fewer options. If I'm going to connect a carbon atom at the end of my rolling with another carbon atom, then I'm limited to a large but finite set of operations. So there's many different species of carbon nanotubes that can exist. They can have different diameters. They can bond. They can terminate one another once you finish rolling in different fashions. Well, the fascinating thing about these carbon nanotubes is that depending on how you roll them up, exactly what angle you roll them up at, their properties are completely different. They can be, for example, one can be a semiconductor and another can be a metal. Now that's incredibly powerful. Now we have a diverse materials set that can serve many different functions. We're just starting from the same building block, this graphene sheet, and we can make it into any number of different things. So that's a great opportunity. And it's a fascinating property of these nanoscale materials. But when you think about electronics, I mean, I've been using words like control. I've been using words like 1 in a billion doesn't work, we're in trouble if a piece of dust lands. Well, the same logic will apply here then, right? If we're going to try to find a way to build a transistor using carbon nanotubes, and there's much progress in doing that, then we're going to have to find ways to make sure that all of our carbon nanotubes are behaving the same as one another. And so hence the need for great purity and great purification. And there's been some very neat work on both finding ways to make all carbon nanotubes the same, and then also very interesting ways of purifying them. I mean, the smartest way to try to purify these nanotubes is to try to purify them based on their properties. So to ask them, to find some kind of technique for querying each one and seeing whether it's got the right properties. And there was some beautiful results published a couple of years ago in which people actually used DNA which selectively would stick to these nanotubes differently, depending on the sequence of the DNA and depending on the roll-up of the carbon nanotube. And so they were able to use that specificity to do some sorting. But it does also imply that when you're talking about, 1 in a billion kinds of perfection, that we may also have to think about a different architectural or conceptual paradigm for building computers going forward. That we may have to think of ways to build computers where not every building block is absolutely identical, where we don't have complete control. When we do that, we can start to utilize nanoparticles, nanomaterials, carbon nanotubes that are similar but maybe not absolutely identical. And then we need to figure out new ways of architecting integrated circuits and programming those integrated circuits in a way that embraces the variability that occurs at the nanoscale. Now, graphene itself, before you roll it up into a carbon nanotube, has actually been a more recent star of the show in nanotechnology. It was the basis, the discovery and the understanding and the properties of graphene was the subject of a very recent Nobel Prize in Physics. And graphene is this very beautiful material. It's got this energy landscape above it that's also very rich and that has surprising properties for the transport of electrons. Electrons behave in weird ways within this two-dimensional, within this planar structure, something that's only a single atom, a single atomic layer thick, where electrons can propagate as waves through this landscape. Now, the challenge, of course, is if you have a sheet of something that's half a nanometer thick, how do you lay your blanket down on something? How do you integrate graphene with a circuit, like perhaps a silicon circuit? Well, there have been a number of advances just in recent years where people have understood how they could put down a single perfect layer of graphene onto a substrate, and thereby they could start to control it. And so the rapid propagation of electrons, the fact that electrons are even more perfectly delocalized in graphene, the fact that they just skim along at incredible velocities over this energy landscape, this is something that people are now exploiting more and more, and that many people are very excited could be the basis for really a considerable extension in Moore's law. You know, one of the other ways of looking at the challenges inherent in extending Moore's law and in building integrated circuits that consistently work well and continue to scale, one of the ways of looking at the problem is that it's actually a problem to do with temperature. The reason why, the reason why is the following: when you crowd all of these little transistors together into smaller and smaller areas, scaling seeks to reduce the power each one utilizes, but nevertheless, the power density, the intensity of generation of heat locally on this integrated circuit, it grows and it grows. And so we're always looking for ways to avoid these leakage currents that we talked about, to minimize the voltages that we need to apply. But there's also a real need for techniques that allow us to whisk away thermal energy with excellent thermal conductors, conductors of heat. And here graphene has shown great interest and great promise as well. Now, there's some very exciting work on using graphene to connect vertically down to the substrate to whisk away the heat laterally within the substrate. Graphene, it turns out, also has these extremely good thermal conduction properties. And so that quality of graphene, not for electron transport, but for heat transport, is starting to be exploited as well. I'd like to finish this lecture with talking about approaches that aren't direct extrapolations of Moore's law or ambitious and challenging longer run extensions of Moore's law, but where instead we say, this nano world, this quantum world, it's weird. Surely it affords us properties, behaviors that we have not used in digital computing until now. Surely there are new ways, revolutionary ways of architecting our computers that can take advantage of this new facility that is offered to us from the nanometer length scale. And so here in this image, I present an example of what's called a resonant tunneling diode. And here we're actually going to take advantage of a current flow in the vertical direction. We're going to leverage the flow of electrons from a top layer through to a bottom layer. We're actually going to use this same tunneling phenomenon that was the bane of our existence in extending Moore's law downward to thinner and thinner gate dielectrics. Well, we're going to use this tunneling to our advantage to make a new class of devices. Let's take a look at how it works. So you can see in this image now a representation with On the horizontal axis, space in angstroms. 1 angstrom is 10 nanometers. And on the vertical axis is energy. And what this is showing is a calculated solution, a model-based prediction for how electron waves are distributed on the left and on the right. Now, the resonant tunneling diode is ingenious. What it does is it recognizes that we can set up an electron in a particular state on the left of a barrier, and we can create a state, really an opportunity for that electron to go to on the right-hand side, and that we can ensure that there is strong coupling between the left and the right only if the electron takes on that particular energy, the resonant tunneling energy. And so what we do in a resonant tunneling diode is we apply a voltage. Applying a voltage is just giving an electron a bit of energy, so we can raise it up in energy. But until it sees this resonant transmission, this tunneling phenomenon, it's not going to go over to the right with any reasonable probability. And so we raise our voltage a bit, and essentially no current flows. We raise it a little bit more, and all of a sudden we become aligned with this resonant state, and huge current tunnels over to the far side of our transistor. Now here's the thing that happens next that is not done within contemporary electronics. We raise the voltage even more, and we become off resonance. We lose the capacity to tunnel resonantly. Our current goes down again. This kind of behavior, instead of looking like what we call a monotonic characteristic, where for more voltage the current just keeps going up, but this kind of behavior where it goes up and then it goes down again, this is a shape of a curve, a shape of what we call a transfer curve that is not currently exploited in electronics. And yet what you can do with that is you can create multiple leveled logic, it's called. You can have many bumps that you engineer through many transfer states, and you can have stable regions within them. And so you can have potentials in currents that aren't just zeros and ones, but you can have zeros and ones and twos and threes. And so in principle, if we can figure out a good way to do computation based on this, we can embed more information inside every transistor. Instead of being limited to binary logic only, zeros and ones, two options, we can give ourselves many more options within every transistor. And so now, our scaling paradigm, instead of being fixed at one pair of states, a binary option, 0 or 1 per transistor, we can scale not purely by just making that entity smaller, but we can scale by enriching the amount of information that can be conveyed or can be stored or can be processed within every building block. Now that in turn hands over from this exciting concept, that hands over to the computer designers, how do you make an integrated circuit on this? And there's certainly progress and there's certainly work, but it remains the case that today the integrated circuits that are used in your computer continue to rely on binary logic. In today's lecture, we've started from the perspective that electronics is, and its evolution over time, is really one way to get at the nano world. That initially in the 1950s and 60s, this opportunity to integrate more and more transistors in this very scalable way onto a single material, to do it monolithically, that this then drove the emergence of aggressive scaling, the emergence of Moore's law. And we scaled down and down and down. And we developed technologies, techniques, methods of fabrication, cleaner clean rooms, to allow us to build things smaller and smaller. And then inevitably we got to the nanoscale. And that is challenging and that is exciting. It's challenging because the rules do change on us. We can't avoid it anymore. As we scale more and more, we start to see these phenomena emerging. And nanotechnology and nanomaterials help us manage those challenges and continue to drive forth within this paradigm. However, no matter how far we go, there will be limits. And this field of electronics and of computing is looking for the next breakthrough. And it's looking to nanotechnology, to the new types of behavior that occur, not just as the problem, as in the first part of today's lecture, but also as the solution that allows us to embrace the behavior at the nanoscale and leverage it towards new paradigms in computation. You remember there was a day not too long ago when there were computers and there was communications, but they were distinct from each other. You'd actually go and you'd sit down at a computer and you'd do some work, but you had no expectation that it was connected to every other computer in the world. Maybe you had a personal digital assistant that you carried around with you in the palm of your hand, but it wasn't tethered to every other PDA, every other computer, to an internet. What is it that happened in the last decade or so that made it possible that information was everywhere? In the previous lecture, pair of lectures, we talked about how electronics has enabled computing, the processing of information at vast speeds and at low costs. Well, the internet is the communications side of that story. It comes down to our ability to send information and receive it with high fidelity and at very low cost per bit. How low is the cost? Well, back in 1971, if you wanted to send a terabit of information, a terabit is about 1,000 movies. It would be a couple of hard drives today. If you wanted to send that data over the network rather than sending your hard drive from Boston to California, it would have cost about $150,000 to do so. Today it costs about 12 cents. In 1930, if you wanted to pick up the phone and have a 3-minute call between New York and London, it would have cost you about $300 in today's dollars. Today that costs us about 20 cents. The key that we'll talk about today to realizing this incredibly low cost per piece of information, per unit, per bit, per binary digit, the key has been fiber optic communications combined with wireless communications. Now, we spoke during the previous 2 lectures really about the basis for wireless communications. This was our ability to make silicon circuits that were very low in cost, that got smaller and smaller, and that got faster and faster and more efficient in their utilization of electrical power. And so it's that success of electronics to microelectronics to nanoelectronics that's the basis for our untethered communications. But there's a backbone, an information-carrying backbone that resides behind the mobile devices that we are all able to carry around with us and achieve continuous communication with. That backbone I'll call the optical internet. That refers to our capacity to send vast quantity of information down what you can think of as pipes for information, and the pipes carry light. So let's talk about these pipes. Let's talk about the optical internet. Here's a picture of a very familiar one of a bunch of optical fibers. So these are pieces of glass, and through each one is independently conveyed a stream of light. And the light is modulated, it's turned on and off, and through that on and off, and through a synchronous measurement at the other end with a detector, we're able to convey information. Now the key to sending a lot of information per second is to modulate that light many times per second. We've seen these familiar pictures before, these glass fibers. I'd like to talk about how they work. What are their properties that are so important? What does that have to do with the materials, the atoms, the molecules that underlie them? But first, onto the structure itself. What does the pipe look like? Well, here's one of these pipes in cross-section. You can see a light ray, which is the red line, bouncing back and forth down this optical fiber. And this idea of bouncing ends up being very important. Light is prone to diffuse. It's prone to disperse. When you think of a spotlight, you have to work hard to try to focus it. But the further away you are from the spotlight, realistically, the more that beam is going to be spread out. But if we're going to communicate information from Boston to California using just one of these small glass pipes, we're going to have to confine the light. And so this is one of the first properties of optical fibers. In fact, we call optical fibers, based on this glass cladding and also a glass core, we call them single mode fibers because there's only one angle at which the light can bounce. We design the shape of this core, which is cylindrical, and we design the optical properties of the cladding that wraps around that core such that light propagates with only one bounce angle and consequently with a single speed, with a single velocity over these very long distances. How do we engineer that quality? Well, this is really all about creating an optical environment in which light has two options. It can either propagate or it can be lost. It can escape. And then our job in creating the source of light and shining a beam of light into one of these optical fibers is to excite only this one mode, only the light mode, where light can just race down this fiber without impediment and at a single well-defined speed. Imagine what would happen if light had a couple of options. Imagine if it could bounce at different angles and therefore make it at different rates. Our signal would disperse in time. It would spread out. And that phenomenon is known as dispersion. And if we're going to try to get as much information packed in as possible, we want to modulate our optical source as rapidly as possible. We can't afford any spreading. Spreading in time would be a loss of signal integrity. We would smudge our signal. We would no longer be able to resolve it. And so the design of fiber optic cables that achieve this very low dispersion is one of the central tenets of successful fiber optic communications. There's another really crucial aspect to the ways in which optical fibers have been designed and have been constructed, and that relates to loss. Clearly, to ensure that our signals go as long as possible without losing information, without losing power, we're required to make this glass as transparent as possible. There's a variety of mechanisms by which light can be absorbed really in any medium. So a first one is what we call band-to-band absorption. And by that we simply mean that the available electronic states, let's say in a semiconductor, those states cannot be successfully breached by light coming in, by a photon having a particular energy. If a photon can come in, shine on a material, take an electron, excite it successfully to a higher energy, if there's a shelf, it can elevate that electron to a higher up energy level, then we will have absorption. Clearly, that's not what we want if we're going to send information over thousands of kilometers. And so optical fibers are designed to have essentially no optical transitions or no electronic transitions available at the energies that we'll be using to send the information with. There's another way to lose light, though, that's not absorption. It's called scattering. And this is the phenomenon that we see in clouds or in fog, where light doesn't actually transfer its energy into the particles of water that make up a cloud or fog. But having this medium, which is a bit different from the air environment, having this little bubble, this little droplet of water suspended in the air, leads light to see a discontinuity, and it ends up with some probability being scattered in another direction. Well, that doesn't make seeing very easy. You can't see through clouds and you can't see fog as a result of the scattering, and it doesn't enhance the visibility of light going down an optical fiber either. So this is all about smoothness. This is all about, it's just like with the clouds. If we were to have an optical fiber that created a path that wasn't smooth, a bit like having a well-paved roadway, then we would have a reason why light could scatter out of its propagating mode rather than stay confined down the pipe. So making these interfaces in these glass fibers very, very smooth and perfect and well-controlled and very homogeneous, making the core material out of a single type of glass, making the cladding material out of a single type of glass, that is another one of the key steps in the development of optical fiber growth that was so crucial in allowing information to propagate such vast distances. Now, there's a particular wavelength of light, or range of wavelengths of light, that are particularly conducive to propagating down optical fibers without loss and without scattering. It really comes from a compromise. On the one hand, if you go to too short a wavelength, too high a photon energy, you're prone to participate in certain scattering and absorption processes. And if you go to too long a wavelength, you're prone to participate in other absorption processes, processes that are more like thermal processes, lower energies, but that can become very abundant once you get down to these very small energies. And so that drives us to kind of a compromise wavelength or a compromise photon energy. And at this wavelength, light can propagate for over a kilometer with almost no loss or scattering loss at all. It's pretty incredible. So imagine if you were to take, say, a window on your home. Is it maybe 1 centimeter or 2 centimeters thick? Well, imagine taking that window, and instead of it being 1 centimeter or 2 thick, it being a kilometer, almost a mile thick, and being able to see perfectly through it. That's what optical fiber technology has achieved for us. This incredible transparency is the basis for being able to convey information over such incredibly long distances. So now we ask ourselves, we have our window, we have our basis for confinement, we have our basis for sending information over these very long distances. Well, where will we get the light from? This light needs to have some very specific properties. First of all, it needs to be something that we can couple into an optical fiber. These optical fibers, in order to achieve their single mode properties, in order to ensure there's only one available bounce angle, only one velocity for light, these optical fibers are quite small. They're about 10 micrometers in diameter. So they're not at the nanoscale. They're more kind of, they're on the optical length scale. But in order to couple into these, we need to make a beam of light that's similarly small. So imagine taking a light bulb that puts light everywhere. It'd be very, very hard to focus much of that light inside. Even with a light-emitting diode, it'd be very difficult to couple most of the light into this very small aperture. Lasers, on the other hand, are famous for having exactly the properties that we're looking for. Lasers provide a beam of light having a single direction. And so they provide us with the opportunity to couple right into this direction that the light will be propagating down in the optical fiber. In fact, their beams can be tailored such that the range of acceptance angles of the optical fiber can be matched by the output of emission angles from the laser. Now that's one sense in which light from a laser is sort of very pure or very perfect. It's the sense in which it's very directional. There's another sense in which laser light is very pure, and that's in the spectral sense. When we're thinking in our wave picture of electromagnetics, we would say that it's got a single wavelength. It's got a single periodic oscillation in time and in space. It's very pure in its spectral content. It would be like singing a single operatic note without any vibrato, a very pure note, very clean note. In our photon picture, in our quantum picture of light, we would say that these colors of light have a single well-defined energy. And that ends up being very important as well because, as I described, the low loss of the optical fiber derives in part from having selected a color of light that's very not prone to be absorbed. It's very unlikely to be absorbed. And so that point about the photon energy is extremely important as well. So this is what we desire. These are the properties of light that we're looking for. But how do we go about generating it? How do we go about building one of these lasers? In fact, if you were to picture a laser that perhaps you've read about or seen on TV, perhaps you've seen pictures of the early lasers that were developed in the 1960s using gases as the medium which transferred energy from the electrical domain into the optical domain. Or perhaps you've seen pictures of lasers that are going to be used to shoot down missiles, incredibly powerful large lasers. You'd think, this doesn't match with the size scale we're talking about. You think, these optical fibers, I have this aperture that's 10 micrometers in size that I need to couple into. How am I going to match that with a laser? Well, it turns out that semiconductors, including semiconductors using quantum effects that have components of them that are nanometer sized, semiconductor lasers have been developed that are extremely small. They're extremely compact. They look a lot like very small chips, very small integrated circuits. And they use the semiconductor itself as the means of transferring energy from the electronic domain, where we're able to pass a current through one of these lasers, into the optical domain. This is how one of these lasers works. The lasers rely essentially on two phenomena occurring simultaneously. The first one is amplification. Amplification is familiar to us. For example, obviously your stereo speakers participate in amplification. They take a very weak signal, a little modulation in the electrical domain, and they turn it into first a much stronger electronic signal, and then that in turn is transduced into an acoustical signal. So amplification, of course, then refers to growing the intensity of signal, giving it more power, but retaining the underlying form of that signal, just amping it up, bumping up the intensity of that signal. So in lasers, the amplification that we're talking about is amplification of light. We're talking about taking a weak optical signal, and a weak optical signal can emerge anywhere at any time within the laser. It's called spontaneous emission, wherein light is always being absorbed and emitted. So there's always little bits of light around. But one of the key components of a laser is to take some of these little stray bits of light that are always coming and going in the real world at room temperature and gain them up, provide them with amplification. So we call this optical gain. That's the first ingredient in a laser. The second ingredient is a resonance. You can also think of this as feedback. In the simplest terms, the front and the back of a laser are both mirrors. They're not perfect mirrors. If they were perfect mirrors, then light generated between those two mirrors would always remain trapped. But if they're just slightly less than perfect mirrors, light is mostly trapped, and then occasionally it can escape out the front facet. It can be transmitted through the front mirror that has a less than unity reflectance. And so within this laser cavity, we have a photon occasionally being generated through a spontaneous process, amplification of that photon where its intensity grows. In fact, it turns into many photons as it propagates through, substantial reflection, and then back and forth as we build up and we build up and we build up this crescendo of light within our laser cavity. Now, eventually, we build up such a crescendo, such an intensity of photons within our laser cavity that the amount of energy we're pumping in electrically to create this gain cannot amplify further. And so we reach what we call a steady state. We reach an average expectation of a number of photons, of a density of photons inside this laser cavity. And while these lasers are very, very small, the length of their cavities are perhaps a millimeter, and their lateral dimensions are on the order of microns. The intensities locally within the most powerful of these semiconductor lasers are amazing. They're about the intensities of light inside the sun. And so within this very small device, we've built up an incredibly high power density using the combination of amplification or gain and feedback or resonance. Now inside this laser, there's some crucial nano-engineered components. In fact, this is the field that brought me into the field of nanotechnology. I was just an undergraduate student at the time. I was studying engineering physics or applied physics. And I loved my physics courses. I loved studying quantum mechanics, solving problems, solving equations. But I thought it got so much more interesting if I could actually see the manifestations of these very exciting, sometimes weird, sometimes unusual concepts that we've talked about together, if I could see them manifest in some kind of device, and where they weren't just present, but they were what we were using. They were what we were taking advantage of. Well, quantum wells, which are at the heart of most semiconductor lasers today, are examples of quantum engineering in order to make a better laser. Let's talk about how they work. So inside a normal semiconductor, the energies that are available, the photons, the energies of photons that can be produced, these energies are determined by the structure of the semiconductor. But that can be quite limiting. There are only certain colors that are available from a given composition of semiconductor. Now, as I described, in fiber optics, there's a very specific wavelength that is our perfect compromise that makes our glass window completely transparent over a kilometer's distance. We need to match that wavelength very, very well. And it's very difficult to find a semiconductor that matches it just right. But in quantum wells, we take advantage of the fact that the electron wave has a physical extent, that it's a cloud, as we've discussed, and we compress it down just in the plane, just in one dimension, to make a confined structure which boosts up the energy of these electrons. We tune it the way one would tune a guitar. We tune the resonance energies that this electron wave experiences. And by tuning them just right, by pushing these energy levels up, we're able to achieve stimulated emission, the process of gain inside our laser, at exactly the wavelength that we need. And so through this quantum engineering, and only because of it, we're able to perfectly match the colors of light that are generated from a semiconductor with those that we desire to achieve extremely efficient, low energy, low cost per bit communications. It's also just worth mentioning that the semiconductors that we use here, they're semiconductors the way silicon is, but they're not silicon. They're materials such as gallium arsenide or indium gallium arsenide. Instead of residing in group 4 of the periodic table, where the elemental semiconductors such as silicon or germanium reside, these are called elemental because only one element, pure silicon, pure germanium, is required to make materials this way. They're in what are called the compound semiconductors. And with the compound semiconductors like gallium arsenide, we combine an element from group 3 and another from group 5. Gallium from group 3, arsenic from group 5. And we combine them together in equal stoichiometry. So thinking back to our periodic table, we've achieved a good match. Group 3 and group 5, they together will satisfy a full electronic orbital, the way silicon, 4 plus 4, will satisfy a full electronic orbital. They also rely on covalent bonding, so they're very, very strong. They're very robust materials. But by introducing another element, by having a pair of elements, or in fact, we can introduce a third or a fourth element from group 3 or from group 5, we have more degrees of freedom. We have more room to engineer the band gap of our semiconductor. So as a result of that, we're able to make materials that are much more agile. They're much more prone to enable us to choose just the right wavelength for the emission of light. But that point about which semiconductor we use in optoelectronics brings us back to a really attractive and exciting opportunity for the field of photonics, the engineering using light, which is researchers have made considerable advances in the last couple of years in figuring out how we could use silicon as an optical material. And that would be very, very attractive. These compound semiconductors that have been the basis for lasers and fiber optics, they work well when you're thinking of engineering discrete components. It's a bit like when we were talking in our electronics lecture about the original transistors, where even in the 1950s and 60s, people were starting to make very competent transistors that could switch, but they had a really hard time connecting them together. Well, the problem with these compound semiconductors is that typically their cost is much, much higher than that of silicon. A component of that is the actual materials themselves and their availability, but another is that silicon, because of the electronics industry, has scaled so much that there's now many, many ways, many different foundries in which to make silicon. And so there's a community of researchers and now companies that feel very strongly that if we could engineer optical materials and devices using silicon, we would be able to make the use of light in communications and potentially even in computing much more widespread. Why is this almost an inevitable trend, an important thing to do? We talked during our discussions of the field of electronics about how as we make our chips smaller and smaller, we put more and more energy density into a given region of that chip. In fact, it's amazing. If you look at the evolution of the energy density of integrated circuits, we're only a few doubling factors away from having the same energy generation density in the very most active part of an integrated circuit as the energy density inside a nuclear reactor. And so we're starting, as we shrink and shrink and shrink in the field of electronics, we're moving towards a denser and denser generation of energy. Now on our chips, of course, our goal is to whisk that energy away and to transport it away as quickly as possible so that our chip doesn't heat up and melt or start to lose performance. But one of the most energy-consuming factors in the operation of a chip today isn't the computing, though that consumes energy too, but it's the communications. And so one of the reasons to be so interested in seeing whether we can integrate electronics, silicon, with optics is that we may be able to make the communications function much lower in its energy consumption by building it on top of a silicon chip. There's a lot of exciting work going on in exactly this area, and there's a couple of pieces to it. So one of them is to be able to guide light around a silicon chip in a manner where it's not lost. It's just like in the fiber optic case. And in order to do this, researchers have recently discovered how to use existing electronics processing, so things like photolithography and etching, which are already utilized to make electronic circuits. Well, they figured out how to make good waveguides out of silicon. And once they figured that out, they actually realized that silicon was an extremely good guide for light. It's almost more like a wire, a tightly confining wire for light, than a fiber optic cable is. Silicon has a very high refractive index. In fact, this is a place where silicon has something in common with diamond. The appearance of diamond, the fact that it's got this beautiful ability to reflect light in many directions when you hit it, and yet it's transparent, that comes from its having what we call a very high refractive index. It's got a high optical density. Well, silicon does as well. And what that means is that if you can get light into it, which is the hard part with something with high refractive index, but if you can get light into it, then the light doesn't want to escape. It's tightly confined. It gets trapped inside. And it's that trapping and the multiple bounces that makes diamond have its characteristic flash of appearance. So in the case of silicon, what this means is that we can make waveguides that can meander across an integrated circuit, can take multiple bends, can go around loops, can go around tight turns, and they can do that very efficiently. And so silicon is proving itself out to be an extremely good mode of conveying light on integrated circuits. So that's looking very promising. Now, another problem, though, was with this high refractive index, it was hard to get light into the silicon waveguides. And there have been recent advances in the design of the regions where we couple light from the outside world into these waveguides called adiabatic coupling, where we kind of go continuously from the size and character of light in the air, and we funnel it down. And it really does look just like a funnel. We funnel it down into the silicon waveguide for convenient conveyance across the integrated circuit. There's another field that's attracted great excitement these days that doesn't even use an optical medium, one of these high refractive index media for the conveyance of light. The field is called plasmonics. And here, researchers are making metal particles that are spaced a defined distance from each other, where electromagnetic waves can hop from one particle to the next particle to the next particle. It's a bit like crossing a stream and having a bunch of evenly spaced rocks that you can use as steps along your way. This has yet to be fully proven out as a practical technology, but it's very much a nanotechnology because the steps, because of light's characteristic size, the steps themselves are measured in the kind of 50 to 100 nanometer range. These are actually the same particles that I was describing earlier when we were talking about stained glass. These particles that were, without even knowing that early artisans were introducing plasmonic particles into stained glass, they were doing so, and they were shaping the color that the glass appeared to have. Well, these same kinds of phenomena are now being used to provide a means of carrying light systematically around an integrated circuit. Where this is ultimately leading to is being able to convey light around a silicon integrated circuit. But the other piece of this is, just like in our fiber optic communications, the ideal thing would be to generate light and to turn it on and off right on the chip. And until about 5 years ago, we hadn't thought of silicon as being an active optical or an active optoelectronic material. It was one that could pass light through itself, but that was about it. But in the last half decade, researchers have found that they can now, using new phenomena, make lasers on silicon, and they can make modulators, which turn on and off optical signals. One of the missing pieces in this field of active silicon electronics is that at the moment, these components are a little bit big. So they end up taking up a fair amount of the real estate of the space on one of these silicon integrated circuits. So the thrust of this field now is to figure out how we can take these laser technologies and modulator technologies, which are now fast enough to be extremely useful in lowering the power burden in silicon integrated circuits, how we can take these new building blocks and condense them even further in order to scale down, just the way Moore's law enabled us to scale down the electronics. We need to proceed with scaling down the optics as well on silicon. In this field of optical communications, it moved so fast. We talked about Moore's law in the context of electronics, where there was this doubling every year. Well, in optics and fiber optic communications, there was a doubling in efficiency or in number of bits that could be sent per second over a given fiber cable. every 18 months. There was an even faster generation turnover. And at one point, when people realized they could put many colors, they could put a rainbow of colors down an optical fiber, there was just a sudden increase of a factor of 10, essentially overnight, with the advent of wavelength division multiplexing. It's these kinds of leaps and bounds advances that led to an optical internet where bits were nearly free. This field of optical communications, building the optical internet, connecting it to the wireless world, it's got a rich set of fascinating physics at the nanoscale. It involves light as a wave propagating down fibers, and it also looks closely at light as a particle, something where we generate in a fundamentally quantum device, the laser, a light that is not absorbed in the fiber and can travel many, many kilometers, in fact, hundreds, even thousands of kilometers, very, very long distances without losing its energy. This has also given us a chance to feature two of the stars of the show in nanotechnology, electrons that are the basis of computation because they love to interact with one another, and photons, which can propagate freely. And many of the devices that enable this are at the junction between the two. They're the ones that allow us to transduce between the electronic domain of the world of information and computing, and the optical domain, the domain of communications. We've been talking a lot about processing information using electronics and nanoelectronics, and about conveying information with the aid of lasers based on nanomaterials like quantum wells. Well, how do we gather this information? Where does this information about our world come from? Light provides an incredibly rich source of information about our physical world. Obviously, our eyes are our most rich, most information expressive sense. To convey that, to convert that into the language of the digital, to feed it into our image processors inside our computers, to feed it into our fiber optic pipes, we need something analogous to our eyes. And that is the world of image sensors. Whereas we've been speaking in the previous lecture about generating light, converting electronic information and power into the photonic domain, we're interested now in the reverse process. We're interested in how we transduce information about the world around us into the electronic domain for subsequent processing and communication. It's pretty incredible what we can do already with our megapixel digital cameras, the ones in our phones, the ones in our larger, more formal photographic cameras, our professional cameras. But in fact, I'll make the case in this lecture that just scratches the surface of the information that we can garner about our physical world using light. In fact, in wavelengths where you and I can't see with our own eyes, there's additional information to be harvested. You know, you can think of any material, any chemical compound, as having a color or having kind of a fingerprint in the spectral domain. We are able to tell what's coming out of a smokestack that's a kilometer or two away by looking at the colors that absorbs, or that it reflects, or that it emits when we stimulate it with light. We're able to look off in the distance at a safe standoff and potentially identify whether something emitted into the air is some innocent spore or whether it's anthrax. We're able to use colors in the ultraviolet to start looking for the early signs of skin cancer. But these are all wavelengths that I just mentioned that your and my eyes don't see. And so here we have the chance to use advances in materials, and specifically in nanomaterials, to perform spectroscopies or to image in wavelength ranges that on our own we aren't able to access. In a sense, we're able to augment our senses using the capacity of imaging and imaging materials. But let's start with what's so ubiquitous now. Let's start with our digital cameras. It's interesting to just step back for a moment and think about film-based cameras, which of course were so widespread and so used, even though now we've converted over to digital. And even in film-based cameras, there was nanotechnology, even though it wasn't deliberately included. The way in which these silver-based films worked was that there were sort of 50 to 100 nanometer sized particles, each independent of the others, in which a photocatalytic reaction occurred. So when a photon came in, there would be many knock-on effects where one of these silver-based salts became soluble. And so the resolution, the spatial resolution of these photographic films was tremendous, and that often comes across in the beautiful images that we're able to generate with film-based cameras. Well, with silicon-based cameras, we're also very focused on resolution, being able to heighten the number of pixels of information that we're able to read out. It's remarkable how we go around now with this camera. It's so small, it's just something that we take with us everywhere because it's embedded inside our mobile handset. And a lot of its advantages, its convenience, relates to its small size, also relates to the fact that it's got a direct interface to information processing, the processor, the integrated circuit inside our cell phone, the many integrated circuits in our cell phone, in fact, and it's also directly linked to the internet. It consists of a lens. The lens has to be a certain distance from the image sensor integrated circuit. That the image is focused using the lens onto that image sensor, and essentially there's just an array of millions of pixels of photodetectors, of light sensors, which are then read out using this integrated circuit. Now, one of the challenges in making these optical modules more and more appropriate for use in cell phone cameras going forward is the fact to make the need to make our cell phones slimmer and slimmer. That's one of the key driving forces for mobile devices. They should be more compact and more convenient. And so there's great interest in being able to make the module slimmer, because today it often limits the thickness of a cell phone. Well, we'll talk in a moment about how using nanomaterials we're able to make image sensors that allow us to build optical modules that are slimmer, more compatible with the mobile form factor. But let's take a look at this picture of one of these image sensors. This is actually rather a large one by comparison. In your large professional digital camera, they can be an inch on side, which is actually quite large for an integrated circuit and leads to higher costs. These sensors are called CMOS integrated circuits, and the CMOS is an acronym for the kind of baseline process that we use throughout silicon electronics. And what it really communicates is the fact that the image sensor industry has been able to take the available processes used to make silicon electronics, normally no light involved, no photons involved in what your typical processor does inside a computer, but it's been able to leverage that capability, those set of foundries invested in making silicon, and it's been able to use that existing resource to build our image sensors. That's been great news for achieving very, very low-cost cameras. But what it also does is it puts the image sensor world onto the Moore's law track. So it means that there's this constant pressure to be able to shrink the dimensions of the components of these integrated circuits and the integrated circuits themselves to become smaller and smaller, more and more compact. That is great news for fitting more megapixels into a given area. But there's some compromises that we'll talk about in a second when you shrink pixels down further and further. The bottom line one is that you end up having fewer and fewer photons impinge on each pixel. So if you're taking a picture with your cell phone camera and haven't always been satisfied, maybe especially if it's in low light, that's a consequence of this shrink down in the number of photons that impinge on each pixel as a result of shrinking the pixel. Let's zoom in on one of these pixels and take a look at it in a little bit more detail. The left image is representing the conventional silicon image sensor approach. At the bottom of a well is the silicon-based light sensor. Now, silicon is not a particularly strong absorber of light. And you can't blame silicon for this. Silicon was not selected as a material because of its optical properties. It's its brilliant electronic properties that has driven the emergence of the electronics industry, all based around silicon. But silicon does also have optical absorption. It's just a little bit on the weak side. So that's one of the first challenges in existing image sensor approaches that use silicon and only silicon to achieve their functions. Now, the other challenge you can also see by looking at this image if you look at what's above the silicon, you'll see various layers of materials. And those are called the interconnect stack. Now, to make an integrated circuit, including an image sensor, we need those wires that we were talking about in our lectures on microelectronics and nanoelectronics. We need to connect together our transistors. In the case of image sensors, we need to reach in and see our pixels electronically. We need to read out what our pixels have seen in the electronic domain. And so we need wires. But now, because we build those wires on top of silicon, and silicon functions as our substrate, we end up putting wires in the way of the light detector itself. So this problem, which is known as the fill factor problem, wherein the area of a pixel is taken up quite a bit by wiring that obscures illumination. This is a problem that has led to deteriorating images as we shrink the size of our pixels. Now here's where nanotechnology comes in. Recent research has shown that we're able to build light detectors that can function, in a sense, the way silicon does, as light absorbers that transduce photonic information into electronic currents. We're able to build these using a new material set, not necessarily even silicon-based, involving quantum dots, what are called colloidal quantum dots. Now these particles, they're semiconductor particles, they're synthesized in solution, they're dispersed in a solution, so they're just like a paint. And you can coat them onto a silicon wafer, and you can coat them on the very top. And so now, as shown with this film at the top level of this nano-enabled integrated circuit, we're able to absorb the light closer to where the light is coming from. The light's no longer responsible for passing through these layers of wire, for passing through an optical aperture, and then being absorbed in the silicon beneath. Instead, we bring our sensor closer to where the light impinges from. So this is a first advantage. This use of nanomaterials overcomes the fill factor problem. The other challenge that it overcomes is that whereas silicon was not engineered in the first place for light absorption, we're able to engineer these quantum dots to be extremely strong light absorbers. So now we're able to make a very, very thin film. It's almost like putting photographic film on top of a CMOS image sensor, and we're able to capture the image up top and then read it using the silicon electronics below. And so this now is a return to using silicon for what it was originally intended for and is so effective for, which is the electronic function. And we've built a second story on top of the silicon using nanomaterials, and this second story now reaches out and senses the light to be read by the silicon beneath. You know, this is also, I think, a great illustration of where some of the greatest opportunities in nanotechnology reside. It's not just in making revolutionary products that are so disruptive that they have nothing to do with previous generations, but instead in overcoming some of the limitations of existing micro-based technologies and augmenting them, but not throwing the baby out with the bathwater, and continuing to utilize the very attractive properties of silicon and silicon electronics, but augmenting them with the distinctive properties of nanomaterials. Now there's another particularly useful property of these quantum dots that bears directly on imaging. And that's depicted in this array of colors that we can see here. These quantum dots can be synthesized to have different sizes. And when we synthesize them to have these different sizes, they can have different colors, different ranges of wavelengths in which they absorb or emit light. And so in this set of beakers of quantum dots, you're actually seeing a set of semiconductor particles that are compositionally identical. The atoms, the elements that are making up these particles are in all cases the same. But their colors, their of absorption and emission, are very much different, spanning the entire visible spectrum depending on the beaker we're looking at here. And the mechanism by which that occurs is the quantum size effect that we've already discussed, wherein if we compress an electron wave down to even smaller than its wavelength, we really squeeze it, well, in that case, we push up its energy levels through the quantum size effect, and we turn it into a blue emitter. Or in the alternative, if we make a somewhat more accommodating quantum dot, if we make our particle of a larger size that doesn't compress or condense the electron wave as much, we no longer push its energy as much up above the bottom of the box. we allow it to take on a lower energy and as a consequence be an absorber of lower energy photons. So this concept is useful in a number of ways. I was explaining how we're so good with our own eyes at seeing visible light, and to a large extent that's what our digital cameras see today as well. Because silicon's wavelength, silicon's band gap, the regions in which it's most prone to strongly absorb light, are substantially confined to the visible wavelength region. But let's look at some examples of where we're able to do new things and see in ways we haven't seen before if we're able to look at wavelengths that go beyond the visible. This image is illustrating the case of a forest fire. And on the right, you see what you can see if you just use your own eyes or a traditional visible image sensor, which is you see a whole lot of smoke. And it doesn't tell you much about where the fire is actually emanating from. It doesn't give people trying to extinguish the fire the detailed information they want to enable them to go straight to the source. But on the left, you can see what happens when you're able to take an image in the infrared wavelengths. As a result of the different interactions of these different wavelengths with the particles that reside within the smoke, we're able to see through the smoke all the way to the fire. And so we're able to get more information about the scene, more information about our physical universe by going to different spectral regimes in the electromagnetic spectrum. Here's another example, this one not to do with fire, but to do with fog. This is taking a picture of the Bay Bridge and then across to Oakland in the San Francisco Bay Area. And on the left, you see the usual view on a foggy day where there's not much to see. But on the right, where instead of using a visible camera, we use an infrared camera, for similar reasons to the case of the smoke, we're able to see beyond the absorption and the scattering of the fog, and we're able to see things that with our own eyes we're not capable of seeing. The connection to the quantum dots is the following. These quantum dot nanoparticles are not limited to only tuning over the visible spectral range like we showed in the beakers. In fact, they can extend all the way to these other wavelengths that have traditionally not been the purview of low-cost silicon-based cameras. Instead, the images that you saw in the previous slides were taken with a much more costly technology. These used the compound semiconductors, things like the gallium arsenide that we talked about in the context of lasers. They used these kinds of compound semiconductor technologies that are able to see out to these wavelengths, but that aren't the basis for very low-cost silicon electronics. What these quantum dots are now doing is taking this very low-cost, high-volume, consumer-appropriate, consumer technology-appropriate building block, which is silicon, and augmenting it and making it capable of seeing colors that exotic semiconductors have seen in the past, but that now we can see with just a top layer of nanoparticles coated on top. Here's another image making another point about the properties of materials and how they're distinguishable from one another based on spectral information. On the left, you see our subject taken with a visible camera, nothing too suspicious, but on the right, you can see which parts of his facial hair are his own and which parts are synthetic. We're able to distinguish between biological materials and synthetic materials using the spectral reflective properties of these different classes of materials. Here's another example of something that we can do when we can see beyond the colors that you and I can see, which is we can create bullet tracer technologies. So we can image a scene, and because the bullet whizzing through the air is so hot, it has a signature, it's actually a thermal signature, that we can resolve with an infrared camera, but that's not available to us using a visible-only camera. As a consequence, we're able to image a scene and not only see where the bullet ends up, but exactly where it came from. So we're able to trace it back to its point of origin. And this is very useful in military applications and also in law enforcement applications. Now, you may have been wondering a bit about how we see color at all in today's digital image sensors. And the answer is that at the moment, we put little arrays of filters on top, optical filters. You can probably picture a color wheel in which we have a red and a green and a blue filter that can transmit those corresponding colors of light from behind a white light source. And those color wheels seek to map onto our own eyes' sensitivity, where we have our color sensing also based on different sensors in our eyes that are differently attuned to the red and the green and the blue. Well, to make a digital camera that can take color images, what we do is we take this array of pixels that we've made on the silicon, and then we overlay that with a little matrix of red and green and blue filters. Now, that works, it's effective, but in doing that, we are throwing away quite a bit of light. When I say a filter, I really mean that we're only letting through our sieve certain photons, say just the green photons, and we're catching within our sieve the red and the blue ones. And so when we do that, we're further reducing the number of photons that end up impinging on each of the pixels within our image sensors. So this is what we call lossy color. It's an approach to seeing in color that does so by throwing away information. And when we're light-starved, when we're trying to take an image in very low light, that's a regrettable thing to be doing. Now, what quantum dots and nanomaterials enable, through their wide spectral tuning and the sharpness of their cutoffs, is they enable a new strategy called stacked pixels, wherein instead of using filters that first throw away light, followed by sensors that sense all colors, they enable the realization of a stacked pixel in which a first top sensor senses the shorter wavelengths, the higher energy photons, and it detects them there. It doesn't just filter them, it detects them, but it also filters them, passing the green, and then a green light sensing layer detects the green photons, and then passes the red, and then a further layer beneath absorbs and senses the red. You can think of this as kind of a perfect pixel, because rather than sacrificing photons, sacrificing information to the cause of sensing color, it makes the best use of every available and precious photon. Nanomaterials have recently enabled a very exciting phenomenon that has been the purview until now really of chemists and physicists. They've enabled researchers to see how we can use this new concept called multi-exciton generation to make better image sensors, more sensitive detectors. And let me start by explaining what this multiple exciton generation concept is, and then how we've managed to use it in order to achieve more sensitive detectors. Multi-exciton generation refers to the fact that normally the way we expect photon detection to occur is in a one-for-one way. One photon comes in, and the best case scenario is that we see one electron worth of information. Now, in today's image sensors, we're often trying to see very, very weakly lit scenes. In fact, we can be interested in getting down to the range where we're only seeing a few photons, a few particles of light impinging on every pixel. In that case, when we only have a few electrons, it starts to become very challenging to read out the information conveyed by those few electrons. We need very, very sensitive low noise circuits to do so. But what if instead we could, for every photon that comes in, what if we could impart multiple electrons worth of information and thereby ease the burden on our circuit? Well, physicists have been studying in these colloidal quantum dots a phenomenon known as multi-exciton generation, wherein every photon comes in and generates not one, but many electrons inside the material. In fact, it's a multi-stage process. Initially, light comes in and does just generate one excited electron. But then there's a little amplification cascade. You might even think of it as kind of a billiard ball knocking into a couple of other billiard balls and generating a number of excited electrons. Energy is still conserved. We need a lot of energy in this primary photon that leads to this primary excited electron that generates this cascade, that generates a couple of lower energy electrons. But the ultimate outcome is that we have achieved gain. We have achieved multiplication from one photon into multiple electrons. Now, until a couple of years ago, researchers had studied this as a fascinating phenomenon, something that occurred with higher efficiency inside confined structures like quantum dots. We were able to enhance the probability of interactions, essentially make more billiard ball collisions occur by putting our electrons into a small box. But they hadn't actually made a device with it. And then in 2009, researchers found that they could make a photodetector that took advantage of this technology. And as a result, they were able to see multiple electrons worth of signal collected in a macroscopic current in something that you could measure using an instrument, an electronic instrument. They were able to see the benefits of this amplification. And prospectively, we should be able to take advantage of it in making even more sensitive image sensors. This is particularly prone to being useful in the ultraviolet because this is where we have an abundance of photons already and an abundance of very energetic photons. And so the ultraviolet is a wavelength range that's prone to excite multiple excitons inside these materials. You know, X-ray detectors are another example of another spectral regime for photons as well, but this one into the very, very high energy range, and where new insights into new materials has led to extremely promising sensors. One of the key challenges and opportunities for the field of X-rays for medical applications is that we would like to get the maximum of information, but with the minimum dose of X-rays. Obviously, we want to get information without imperiling the patient. In fact, sometimes these days doctors choose not to take X-rays in order to avoid overexposure, but as a result, they're surrendering a greater amount of information they could learn about their patient to do a better diagnosis and ultimately a better treatment. And the advent of digital mammography, digital X-ray technologies has led to even more sensitive X-ray imaging systems that have allowed us to reduce dosages and therefore either enable us to take fewer risks with patients in X-ray exposure, or to put it another way, to perform X-rays a bit more liberally and therefore get more information about the patients. This arises again as a result of being able to achieve these single photon detectors, very sensitive detectors for light. The other great advantage, of course, once we get our information, be it visible or ultraviolet or infrared or X-ray, once we get it off of these image sensors, is that we immediately have the capacity to connect it into a computer, to get it onto the internet, or to use the information and to process it, to use machine recognition or image recognition to work up these images, and in the case of X-rays, to give the physician more information than he or she would otherwise have. Let's talk about another spectral regime, one that's just emerged from having been a no man's land. As you can tell, it seems like whenever we enter into a new spectral regime, new information becomes available to us. A different set of colors becomes reflected and transmitted. Another one is now emitting. And so we're able to achieve contrast, distinction based on chemical properties, compositional properties. Well, one of these spectral regimes that until now has been very hard to access is known as the terahertz. The megahertz range is familiar because when you tune your radio in your car, you'll often see megahertz frequencies. The gigahertz is quite familiar because that's the basis for your cell phone's communications. And then as we go to much, much higher frequencies than that, we get into the optical frequencies, the infrared and the visible and beyond. But in between the gigahertz and the optical is the terahertz regime. And until recently, the reason why we had little information in the terahertz regime is that we weren't able to make efficient sources of terahertz radiation. So this is where quantum mechanics has come to the rescue recently. A new class of lasers and light sources and photodetectors have all been realized based on quantum phenomena that allow the creation of terahertz photons. And this is a bit like a waterfall or a cascade. In fact, it reminds me of when I was in the Black Forest in Germany, and I saw an ad for going to the highest waterfall in Germany. I thought, wow, this is going to be pretty impressive. And it was beautiful, but it actually wasn't a single drop of water over 163 meters. It was over 7 sequential cascades. And so this notion of the cascade, where we go down one level and another level and another level, each of those levels, in the case of these cascade lasers, the same height, each of these cascades produces these relatively small energy photons inside the cascade laser. And the way in which this is achieved is using quantum phenomena, using quantum states. where by putting, again, our electrons into a box, we take advantage not just of the first level, the lowest lying electronic level, but there are in fact many levels of electronic energy states that are available inside a box. And then we can couple many boxes together and achieve this sequential cascade, achieve a waterfall of electrons falling down. And every time an electron falls down one of these levels, we see the emission of a photon, of a particle of light that we can use in terahertz imaging. Terahertz imaging is now coming up in security applications because it turns out you can see through fabric, and so that's transparent or transmissive, but you can see whether somebody's concealing either something metallic, like a weapon, or you can even get information on the chemical composition of what's behind the veil, and so you can learn about the presence of things like drugs based on their terahertz signatures. Let's talk about one final example of where this could all go. The field of imaging at a standoff has been taking advantage of the fact that you can shine a beam of light over miles, kilometers, and you can image from a distance for a while. And we've been using spectral signatures to see at these distances, to see chemical compositional information at these distances. But sometimes the kinds of molecules we're looking for are too subtle, too complex. Their spectral signatures seen from kilometers away can't be discerned. And so there's an emerging field for biodetection at a standoff, where we're looking for very, very specific and subtle differences between two organisms, such as whether something is anthrax or whether it's just posing as anthrax. Scientists have come up with new ways to launch an aerosol into the region of the posited threat, have binding occur between nanoparticles that themselves contain a distinctive fingerprint and the subject of interest, let's say the anthrax bacillus, and only if the particles are sticking to the subject of interest do they change color. They take on a different light-emitting color that can be detected from these very, very long distances. So as a result of that, we're able to do, from a safe distance, from a safe standoff, we're able to do biosensing or biodetection using light, but we're able to see more than what you can see if you only sent photons in. Instead, by sending particles in that change their behavior, change their optical spectral signatures as a function of what they're stuck to, what they're bound to, we're able to see much more than the purely spectral fingerprints would allow us to see. The examples that we talked about today, they're about really coupling and interfacing the optical with the electronic. They're about using nanotechnology as a basis for transduction, now from the optical into the electronic. The way they leverage nanotechnology first and foremost is through their capacity to engineer materials and their properties towards a particular application. It's our ability through nanoengineering to tailor the properties of materials to our desires, to particular spectra, to being strongly absorbing, to being readily integratable with conventional silicon platforms that has led to some of the most exciting work in this field. And it also illustrates the point that whereas nanotechnology may sound exotic or new, some of its most powerful and practical applications will come from using nano where we need it and building upon well-established technological platforms such as the field of micro and nanoelectronics, where these are the most powerful solution.